agrochemicals are important ingredients for achieving global food security. However, the need for periodic application stemming from the huge losses witnessed due to volatilization, photodegradation, leaching and surface migration may render agrochemical usage economically unsustainable. Moreover, heavy usage of agriculture chemicals has led to serious ecological pollution. Agrochemical formulations which combine minimum amount of active ingredients with prolonged efficacy would effectively reduce post-application losses. Important ways to achieve this are by photostabilization and slowing the release of active materials. Controlled release formulations of pesticides are retarding repositories which release their biologically active constituents into their environment over a defined period of time. In these formulations, these substances are chemically bound or physically incorporated in a polymer matrix by means of different techniques. The migration of the substances is therefore preceded by chemical reactions for bond cleavage or physical transport processes in and through polymers, which can be mathematically modeled. While in the meantime, there are quasi-standard methods for physical, chemical laboratory test, biological activity test are often performed in the field under conditions, closely approximating actual application. Several of these formulations have already achieved commercial status. The reduction of the toxicity of the substances and of undesirable side effects on non-target organisms as well as the prevention of premature disappearance of the active substances from the place of application as a result of degradation and transport processes under environmental conditions are the prominent characters of these formulations. Opposed to these, there are several disadvantages such as the increased buildup or resistance. In this episode, we will study about the controlled release formulations, controlled release fertilizers which is also abbreviated as CRF, controlled release formulations for improved management of nutrient application, polymers in controlled release agrochemicals and herbicide formulations. First one, controlled release formulations. Recently, controlled release technology has emerged as an alternative approach with the promise to solve the problems accompanying the use of some agrochemicals, while avoiding possible side effects with others. It is hypothesized that controlled release methodology, if widely used in the application of agricultural chemicals, would allow the increased production of foodstuffs while simultaneously allowing a decrease in the amounts and types of agents used. Also, controlled release technology would assist in improving protection for stored grain against insects and rodent pests. It might subsequently reduce the concentration required for beneficial effects and thus avoid or reduce the undesirable side effects of conventional agricultural chemicals. It might reduce the unit cost of materials applications and the expense of repeated and over application of the materials. The overall aim of controlled release formulation consists of protecting the supply of the reagent and to allow its automatic delivery to the target at controlled rates to maintain its concentration within an optimum concentration over a long period of time. Controlled release may be defined as a technique or method in which active chemicals are made available to a specified target at a rate and duration designed to accomplish an intended effect. Usually, Biologically active agents are administered to a target systematically or topically at a site somewhat remote from the target. This results in non-specificity and the need for periodic applications both in case of drugs and agrochemicals. Remote application, besides increasing the cost of treatment, often produces undesirable side effects either to the target or its environment. Controlled release allows the optimum concentration of active agents to be maintained within the system over a period of time and may allow specific targeting. Second one, controlled release fertilizers. This is also abbreviated as CRF. An ideal fertilizer supplies the nutrient required for optimum plant growth during the entire growing season and has reasonable cost benefit ratio and minimum adverse effect on environment. Three widely accepted practices in order to enhance the efficiency of nitrogen fertilizers are employing slow or controlled release fertilizers. Next one, following cultural practices such as deep placement and incorporation of the fertilizers with soil. Next one, inhibition of microbial activity to minimize conversion of ammonium ions to nitrate ions and or urea to ammonium ions. Slow or controlled release is a newer method and formulation of ideal fertilizers based on this technology has been attempted by many research groups. Slow or controlled release property for fertilizers is achieved mainly by two methods. First method, coating or encapsulating the fertilizer in water insoluble or sparingly soluble and inert materials. Second method, synthesizing fertilizer with slow dissolution as in the case of condensing urea with various aldehydes. Several polymers of synthetic and natural origin and many inorganic substances have been found useful for coating fertilizers. Release of fertilizers from these coated granules is mainly associated with one or more of the following mechanisms such as: first one, water vapor entering the core dissolving the fertilizer and coating burst due to internal osmotic pressure build-up. Second one, degradation of coating by microbes or other environment agents and subsequent penetration of water into the core through the degraded portion. Dissolution of the fertilizer and subsequent emission. Third one, movement of water to the inner core, dissolution of fertilizer and subsequent evolution of the solution to outside controlled by micropores of the coating. Disadvantage of the first two mechanism is that once the coating membrane bursts or degrades, fertilizer release will be very fast. The third mechanism is very much useful in slowing down the release of fertilizers as water enters to the core through tiny pores and subsequently fertilizers come out to the soil. Here the rate of release is rather steady comparing to the other types, and in some cases the rate is found to be gradually declining. Usually temperature influences the rate of release of such systems. As temperature increases, pressure builds up in the core. Subsequent release also is accelerated. However, this is beneficial for the plants since as temperature increases, plant absorption of nutrient also increases. Thus, the system can adjust somewhat the available nutrient in soil as per the plant requirement. In such type of systems, usually the release is independent of pH and microbial activity. Several materials are used for such coating: resin, plastic, lac, silica, sulfur, natural rubber, polyolefin, starch and gypsum were reported to be used for preparing controlled release urea fertilizers. One of the first commercialized and extensively studied slow release fertilizers are sulfur coated urea. This is also abbreviated as SCU. Urea granules uniformly coated with sulfur followed by a wax coating to seal any pores or cracks of the first coating is found to have slow release property. The efficiency of the product depends on the size of the urea pill or granules and the thickness of coating. The release from sulfur coated urea has been reported to take place by one or more of the following mechanisms. They are biodegradation of either wax or sulfur or both coatings. Second one, conversion of amorphous polymer sulfur to crystalline form results in the creation of cracks and pores in the coating. To reduce the microbial attack on the coating, sometimes microbicidal agents like coal tar is added. Environmental parameters like temperature and moisture can also influence the release rate. Other parameters which affects the release rate are thickness of coating, placement of granule and time of contact with the soil. There are several reports on the field performance of sulfur coated urea. It is found to be very effective for turf and forage grasses. It is reported that when high amount of uncoated urea is supplied to Bermuda grass turf is merely destroyed the turf, whereas ammonium nitrate caused moderate burning of the foliage, while SCU, that is sulfur coated urea, caused no damage. Similarly, application of uncoated urea at 112 kg per hectare to corn seedlings destroyed it, while sulfur coated urea at the same rate caused no damage. Sulfur coated urea is also reported to be an excellent nutrient source for ornamental plants in pots. Experiments on corn indicated that on sandy loam and loam soils where irrigation practices were carefully adjusted to prevent leaching losses, corn yield and nutrient recovery with a single application of sulfur coated urea was on tar with 3 split applications of uncoated urea. Single application of sulfur coated urea resulted in more yield and more evenly distributed forage and protein than due to 3 split applications of ammonium nitrate and nitric phosphate. Observations were similar in crops like sugarcane, citrus and rice. The major disadvantages of sulfur coated urea are the sulfur coating, as not very abrasion resistant, may crack during shipment. Sulfur oxidizing organisms metabolizes sulfur to produce sulfuric acid, hence soil acidification may also take place. Inclusion of biocide in wax coating is necessary. Otherwise, rapid microbial attack on the sulfur coating occurs and results in fast dissolution of urea. However, this enhances the cost further. In countries like India, where sulfur is being imported, the manufacture of sulfur coated urea is difficult. One possible way to improve nutrient and particularly nitrogen use efficiency while reducing the environmental hazards is by using controlled release or slow release fertilizers. Compared to the large amount of fertilizers used throughout the world, the total use of slow and controlled release fertilizers, which is also abbreviated as SRFs and CRFs, is still small. In 1996 to 1997, the estimated use of CRF or SRFs was about 5,60,000 tons worldwide and about double this amount of processed organic products. Indeed, the use of controlled release fertilizers has almost doubled over the past decade, but still comprises only about 0.15% of the total use of nutrients. The greatest consumption and production of CRFs or SRFs is in the US, Canada, Japan and Europe. The largest proportion of these fertilizers is consumed in non-agricultural markets, example for lawn care, golf courses, landscaping, with the annual increase in demand above 5%. The use of CRFs in agriculture slightly exceeds 10% of the total amount of CRFs in use, but the demand increases impressively at the annual rate of about 10%. The possible contribution of slow or controlled release to the improvement of nutrient supply management while minimizing the environmental, ecological and health hazards. To enable a better understanding of CRFs, they are classified according to mechanisms of action and production technologies. Attention is paid to their modes, length and patterns of release, quantitative description and significance for improved utilization of CRF or SRFs. Special reference is made to assess agronomic and environmental benefits and to efforts in improving the characterization and standardization of CRF or SRFs. Next module, polymers in controlled release agrochemicals. The different classes of polymers, namely elastomers, plastics and fibers, are extensively used in agriculture for varied purposes. The major application fields include CR pesticides, herbicides and fertilizers, soil conditioning, plant protection, seed coating and gel planting. A number of CR agricultural chemicals had been successfully tested and are commercially available. Controlled release agricultural chemicals other than fertilizers are discussed initially. Crops and livestock are produced in a hostile environment comprising approximately of 50,000 species of fungi, 30,000 species of competing weeds and over 10,000 species of insects, in addition to the grain devouring birds and rodents. The biologically active chemicals have been very effective in suppressing the undesirable weeds and insects, thereby in an increased food production. However, the use of such chemicals should not create any adverse effect on man and his environment. For example, use of DDT, a pesticide with very long life, is undesirable since its residue enters the food chain. On the other hand, pesticides with very short lives do not serve the purpose. Moreover, these materials are susceptible to leaching by rainwater, removal by evaporation or by rapid biodegradation into inactive components. These lost chemicals contaminate the groundwater and are a threat to aquatic and wildlife. In such cases, large excess of these costly active chemicals are applied grossly to compensate the losses. In situation like this, the CR technology can offer much of the save the costly chemical and the environment. Moreover, the desired action can be prolonged. Many of the active biological agents are effective at very low concentrations. Different CR formulations having varied release profile had been synthesized by incorporating these chemicals either physically or chemically to the polymers. Next module, herbicide formulations. Herbicides are rarely applied in the form in which they have been synthesized. Along with the active ingredient, substances are added to fulfill regulatory standards without diminishing the effectiveness of the active ingredients. Likewise, this active ingredients is combined with other materials such as solvents, moisturizers and adherents. The product obtained constitutes the herbicide formulations as usually commercialized. Herbicide formulations have the following objectives. They are to obtain an high biological effectiveness throughout the time required to control harmful weeds, to enable the management and application of herbicides, to reduce the use of solvents and or select solvents that are dangerous or toxic, to minimize or avoid the adverse environmental effects on organisms that are not the cause for herbicide applications, that is fish, crops, etc., to ensure safer use of herbicides by workers and users, to extend the range of herbicide application and to be physically and chemically stable through time and at the same time compatible with other formulations that would be present in mixing systems of the application equipment. The adjuvant or coadjuvant present in the herbicide formulations or during mixing in the tank of the application system are necessary to reach the objectives mentioned, as they are able to favorably modify the physical chemical properties of the active ingredients. The adjuvants may be classified as adjuvant activators or adjuvant modifiers, although many can be included in both categories. Adjuvant activators increase the biological activity of the herbicide. The following are the main adjuvant activators: surfactants and their combinations. These are substances that reduce the surface tension existing between two surfaces that would otherwise repel each other. Surfactant improves the contact of herbicide solution drops on leaves, improving penetration. The speed and total amount of herbicide penetrating the cuticle is related to the concentration and the chemical structure of the surfactant. According to Seaman, surfactants improve herbicide penetration primarily through solubilization, hygroscopic water retention, co-penetration and modification of cuticle permeability. Vegetable oils and minerals, sometimes adding light oils to aqueous solutions of certain herbicides, increases the foliar action of these products. Oils are normally mixed with emulsion or with tense active products, that is 1 to 2%, as they facilitate oil dispersal in water. Vegetable oils and minerals are used in 1% solutions depending on the type of herbicide and oil. Oils may be mineral or vegetable in origin, such as oil derivatives or methylated vegetal oils. These are defined as any substances or chemical, natural or synthetic mixture contributing one or several nutritive elements essential for normal vegetative plant growth. In addition, it has been observed that fertilizers containing ammoniacal nitrogen may increase the effectiveness of some herbicides. Example, bentazone, dicamba and glyphosate. Conclusion: agriculture that protects people and the environment does not rely on toxic pesticides. On the contrary, diverse and healthy agricultural ecosystems free of toxic chemicals of providing nutritious food and a safe environment.